Everyone asked the wrong question about dinosaurs. The wrong question is, how big were they? The right question is, how were they possible? Because the moment you sit down with the actual numbers, the weight, the bone geometry, the height of the neck above the heart, the ground forces during locomotion, the dinosaurs stop being impressive and start being suspicious. They look like they shouldn't work, and when something looks like it shouldn't work, but clearly did, that's not a mystery about the animal, that's a test. The universe is handing you a problem and asking whether you understand the rules well enough to solve it. Most people walk past the skeleton in the museum and feel wonder. I look at it and feel the itch of an equation that hasn't been balanced yet. So let's balance it. Start with something Galileo understood in 1638, not Darwin. Not some 20th century biomechanist with a computer model. Galileo Galilei, working without calculus, without electron microscopes, without any fossil record to speak of, figured out the central problem of large animals just by thinking carefully about geometry. When you scale something up, make it bigger in all directions by the same factor, different properties change at different rates. Length scales linearly. Double the size of something, its lengths double, but area scales as the square of length. Double the size, and areas go up by a factor of 4. Volume scales as the cube. Double the size, and volume, and therefore mass, goes up by a factor of 8. Apply this to an animal. The strength of a leg bone, its ability to support weight without snapping, depends on its cross-sectional area. The weight the bone has to support depends on the animal's volume. So double the linear dimensions, the bone gets 4 times stronger, but the animal gets 8 times heavier. The bone is now carrying twice the load per unit of cross-sectional area. Double the size again, 4 times the original linear dimensions, and the bone is carrying 4 times the load per unit area. Keep going and eventually the bone fails. Not because the material changed, because the geometry is merciless. Galileo understood this completely. He said if you want a big animal to work, you can't just scale up a small one. The bones have to get disproportionately thick. He drew sketches of bones a giant man would need. Stubby, massive, nothing like a normal human bone. He was right. Go look at an elephant's legs, then a gazelle's. The gazelle has slender, elegant columns of bone, thin relative to their length, built for speed. The elephant has legs that look like architectural pillars, nearly vertical, enormously thick relative to their length. Not because elephants evolved aesthetically differently, because at 5,000 kilograms, the gazelle body plan produces bone stresses that would cause immediate structural failure. The elephant's legs are what physics requires at that scale. There is no other option. Now take the elephant and multiply by 10. That's a Brachiosaurus, Brachiosaurus bransii. The mounted skeleton in the Museum für Naturkunde in Berlin is 26 meters long and roughly 12 meters tall at the head, about 4 stories. Modern volumetric estimates cluster between 50,000 and 60,000 kilograms. Call it 56,000 kilograms. That's 56 metric tons, about 8 African elephants. Here is the first suspicious thing: that animal stood up every day. Bone has a compressive strength of roughly 170 megapascals. That means if you apply a compressive load of 170 million newtons to a bone with a cross-sectional area of 1 square meter, it fractures. Below that, it holds. Real bone in a living animal typically operates at a safety factor of 2 to 4, meaning normal activity stresses the bone to roughly a quarter to a half of its failure load. The ceiling is real and it doesn't care how impressive the animal is. You can actually do the stress calculation for a Brachiosaurus femur. Paleontologists have measured the femur dimensions from real specimens. For large sauropods, the cross-sectional area of the femur shaft runs around 600 to 800 square centimeters. Take 700 square centimeters, 0.07 square meters. During slow walking with 2 feet on the ground, each hind leg supports roughly half the body weight. Half of 56,000 kilograms is 28,000 kilograms, or about 274,000 newtons. Stress is force divided by area. 274,000 divided by 0.07 gives roughly 3.9 megapascals. 3.9. Against a failure threshold of 170. That sounds like enormous margin until you realize the calculation assumes slow, steady walking with both feet on the ground simultaneously. Any dynamic loading, acceleration, uneven terrain, one leg bearing more than its share, and that margin shrinks fast. The animal was carefully engineered to be just sufficient, not lavishly overbuilt. And that word engineered is the interesting one. The Brachiosaurus didn't have engineers. It had selection pressure, which is a slower and more brutal process that achieves the same result, structures that work with nothing wasted. The vertebrae are pneumatized, hollow, shot through with air spaces connected to a respiratory air sac system, exactly like modern birds. A solid sauropod vertebra of the right structural size might weigh 40 kilograms. The real ones weigh 7 or 8 because most of the interior is air, with internal bony struts providing structural support at minimum mass. This is the solution aerospace engineers arrived at independently for aircraft design: maximum stiffness, minimum weight, internal bracing. The dinosaurs' lineage found it first by the method of eliminating every individual whose skeleton was too heavy to support itself across an entire reproductive lifetime. Physics wrote the requirement. Biology, across millions of generations, found the answer. They're the same answer. Now here's where the suspicious feeling really sets in. The neck. Brachiosaurus held its head based on the articulation of the cervical vertebrae and the angle of the joint surfaces at a height of roughly 9 meters when standing normally. The heart, sitting in the chest cavity, is perhaps 3 meters off the ground. 6 meters of vertical distance between heart and brain. The physics of pumping blood upward is not complicated. Pressure equals density times gravitational acceleration times height. Blood density is about 1,060 kilograms per cubic meter. Gravitational acceleration is 9.8 meters per second squared. Height is 6 meters. Multiply it out, you get about 62,000 pascals, which converts to approximately 465 millimeters of mercury, 465 millimeter Hg. A human heart generates about 120 millimeter Hg at systole, enough to push blood roughly 1.6 meters upward, which is all we need because our hearts are close to our heads. A giraffe, 2-meter neck cardiovascular system specifically modified for the problem, generates about 280 millimeter Hg. Its heart is proportionally enormous. Its blood vessel walls are reinforced. It has pressure-regulating mechanisms in the neck vessels to handle the sudden redistribution when it bends down to drink, because if you're running 280 millimeter Hg toward the brain and you lower the head by 2 meters, the pressure surge is enough to cause serious damage. Brachiosaurus needed 465 millimeter Hg. That's not a giraffe problem. That's a different category. And here's where I have to be straight with you. We don't know how they solved it. The solution was made of soft tissue, heart muscle, vessel walls, pressure-regulating structures, and soft tissue does not fossilize. We have the skeleton, which gives us the geometry, which gives us the pressure requirement, which is precise and non-negotiable. We do not have the plumbing. Hypotheses exist. Maybe the neck wasn't usually held fully vertical. Some researchers argue the skeletal range of motion indicates more horizontal carriage, reducing the pressure requirement substantially. Maybe there were accessory pumping structures along the neck. Maybe the cardiovascular physiology was tuned to exactly this problem over millions of years. Maybe all three. What we can say with certainty is this: whatever solution existed, it obeyed the same pressure equations we just used. The 465 millimeter Hg requirement doesn't flex because the animal is impressive. The physics doesn't make exceptions. The solution existed. Brachiosaurus existed for a very long time in large populations across multiple continents, and therefore the solution was real, and it worked within the laws we know, and we just can't see it yet. That gap between the physics says this problem is real and we can't yet see the solution is not a failure of physics. It's a statement about what fossilizes. The skeleton turned to stone. Everything else had the decency to disappear. We work with what remains. What remains, in some places, is footprints. And footprints are more interesting than they sound. A fossilized trackway, a sequence of preserved footprints in ancient sediment, is quantitative data. The depth of the impression tells you the pressure exerted by the foot. The area of the footprint gives you contact area. Pressure times area gives you force. From the spacing between footprints you get stride length, and from stride length and leg length you extract speed. These aren't loose estimates, they're measurements. There's a number called the Froude number that governs gait in all legged animals, and it's one of those dimensionless quantities that unifies things that have no obvious right to be unified. For locomotion, it's roughly the square of speed divided by the product of leg length and gravitational acceleration. It captures the ratio of inertial force to gravitational force. And here's the thing: every legged animal, mouse, horse, elephant, transitions from walking to running at a Froude number of approximately 0.25. Not similar, the same number, across animals spanning 6 orders of magnitude in body mass that share no relevant evolutionary history, that have completely different skeletal architectures. It's the same number because it's not a biological number. It emerges from the mechanics of how a leg acts as an inverted pendulum during the walk cycle. The physics is universal, so the threshold is universal. An alien scientist arriving on Earth would have this number in their notebooks before they landed. They would not be surprised to find it in a sauropod trackway. They would be surprised if they didn't. From the actual trackway evidence, large sauropods were moving at Froude numbers below 0.25, speeds in the range of 4 to 8 kilometers per hour, a walking pace, which makes complete mechanical sense. A 56,000 kilogram animal running, all feet off the ground simultaneously, would generate ground reaction forces of 3 to 4 times body weight through each leg at foot strike. That multiplies the femur stress by a factor of 3 or 4. The safety factors disappear, the bone fails, so sauropods didn't run. Not because they were sluggish, because the mathematics of bone strength at that mass forbids it. The trackways are the fossil record confirming the calculation inscribed in stone. Tyrannosaurus rex is the more contentious test case, because the whole cultural image, movies, museum dioramas, decades of popular science is of a fast pursuit predator. The running T-Rex is maybe the central icon of popular paleontology. The biomechanics are more interesting than the icon. A large adult T-Rex weighed roughly 8,000 to 9,000 kilograms. The question of speed comes down to the same bone stress argument. The leg bones have a specific cross-sectional geometry. That geometry has a specific load-bearing capacity, and running generates forces that scale with speed and can be calculated. If the required force exceeds the bone's capacity, the animal cannot move at that speed. The bone is not negotiating. Multiple research groups have run this calculation using different methods: cross-sectional geometry of the femur and tibia, whole-body computer models, scaling comparisons with living animals. The results cluster around 12 to 28 kilometers per hour for large adults, with many analyses concluding T-Rex probably couldn't run at all in the strict mechanical sense. No aerial phase, no moment when all feet are simultaneously off the ground. It walked very fast. Not the same thing as running, mechanically speaking. That conclusion doesn't come from guessing about behavior or making assumptions about ecology. It comes from measuring bones that exist in the actual fossil record and applying stress equations you'd apply to any engineered structure. The biology reduces to the physics, and the physics gives you an answer, and the biology has to honor it. The reason the movie T-Rex runs is not that paleontologists thought it ran. It's that a fast-walking T-Rex is cinematically less satisfying. The physics was there all along. Now I want to show you what I think is the most remarkable thing in all of this, and it's not about any single animal. When biologists see two distantly related species with similar features, they call it convergent evolution and describe it as nature finding the same solution twice. That framing gives evolution too much credit for creativity. The deeper version is physics permits a small number of solutions and selection pressure finds them. Sauropod vertebrae are pneumatized, hollow, air-filled, internally braced. Modern birds have pneumatized bones too, not because birds inherited it from sauropods. Bird pneumatization evolved independently in a completely different lineage. It evolved because at the relevant scales of mass and structural requirement, the alternative produces a skeleton too heavy to function. The constraint is physical. Physics forces the solution. Evolution, whether in a sauropod lineage or a bird lineage, encounters identical constraints and is driven to the identical answer. There aren't 10 solutions, there might be 2, and life across hundreds of millions of years and wildly different lineages keeps finding the same ones because they're the only ones the physics permits. Columnar limb posture. Vertical legs, nearly straight, acting as load-bearing pillars. Elephants have it, hippos have it, sauropods had it. None of these groups share the relevant common ancestor. It evolved independently each time. Body mass crossed the threshold where bone stress in angled limbs becomes unsustainable. The threshold is identical for an elephant and a sauropod because it's a function of gravitational acceleration, bone material properties, and geometry, none of which changed between the Jurassic and the present. This means the physical constraints on large terrestrial animals are tight enough that the space of viable body plans is genuinely small. You could derive what a 50,000 kilogram land animal must look like from first principles without a single fossil, just the equations, and the result would look like a sauropod. Then you look at the fossils, and they're exactly there. That's not a lucky coincidence. That's what it looks like when the physics is real. There is a ceiling, and it matters. The largest land animals in the fossil record, the biggest titanosaurs, had masses estimated around 70,000 to 80,000 kilograms. Patagotitan majorum, described from Argentine fossils in 2017, comes in at roughly 69,000 kilograms. Argentinosaurus, still debated but probably real, perhaps 70,000 to 80,000 kilograms. Nothing terrestrial has ever substantially exceeded that range anywhere in the fossil record at any point in 500 million years of complex animal life. This is not a coincidence. The square-cube scaling argument has a hard implication. At some body mass, the bone required to support the animal becomes so massive it constitutes most of the animal's mass itself, leaving insufficient room for muscle, organs, and the systems that keep it alive. Before you reach that absurd limit, converging practical constraints, metabolic rate, food intake, the time cost of gathering enough food, close in from other directions. These constraints converge on an upper limit somewhere in the range of what the largest sauropods achieved, and there the record stops. Not because evolution ran out of time or ambition, because physics ran out of room. That upper limit is calculable from first principles. You don't need the fossil record to predict where it should be. You can derive it from bone material properties, metabolic scaling laws, and the energetics of locomotion. Then you look at the fossils, and the largest animals in the record are right there, not below the limit by comfortable margin. At the edge, the universe set a maximum size for a land animal under Earth's gravity. Life found that maximum and pushed against it for 100 million years and never went through it, because you cannot go through it. That's not a biological fact, that's a physics fact that biology is forced to respect. Here's something that was wrong for 100 years and then got corrected, and the correction matters because it changes the mechanical picture entirely. For most of the 20th century, dinosaurs were assumed to be ectotherms, cold-blooded, metabolism dependent on external temperature, like modern lizards. The reasoning was pattern matching. They looked like reptiles. Reptiles are cold-blooded, therefore dinosaurs were cold-blooded. That's not evidence. That's assumption, wearing the mask of evidence. The measurements that overturned it came from bone microstructure. When you section a bone and examine it under a microscope, you can read the deposition rate from the tissue architecture. Cold-blooded animals grow slowly and produce microstructure with distinct growth rings. Warm-blooded animals grow fast year-round and show fast-deposited fibrolamellar bone. High vascularity, different organization. Dinosaur bone microstructure looks warm-blooded. The large sauropods and theropods show bone consistent with fast, sustained growth. Birds and mammals, not lizards and crocodiles. Oxygen isotope ratios in fossil bone added independent confirmation. The ratio of oxygen-16 to oxygen-18 incorporated into bone mineral depends on body temperature in a precise calibrated way, a real thermometer embedded in the fossil. Results for large sauropods indicate elevated body temperatures well above what passive solar heating could achieve. These animals were generating heat internally. Why does this matter mechanically? Because metabolic rate determines energy budgets. A warm-blooded Brachiosaurus needs a resting metabolic rate, perhaps 10 times higher than a cold-blooded one, of the same mass. That changes food requirements, daily movement patterns, muscle physiology. Metabolism and mechanics are not separate questions. The assumption lasted a century because nobody made the right measurements. When the measurements came, the assumption collapsed. Data disagrees with you. You change what you think. Let me tell you what we genuinely don't know, because honesty about ignorance is more useful than false confidence about knowledge. We don't know the soft tissue. The cardiovascular solution to the Brachiosaurus blood pressure problem is gone. The actual muscle architecture is gone. Attachment points can be inferred from bone scarring, but real volumes, fiber types, force-generating capacity cannot be read from bone alone. How Brachiosaurus regulated blood pressure dynamically as it raised and lowered its head, gone. The nervous system, entirely gone. We don't know behavioral ecology with any real confidence. Trackways give us speed and gait. They don't tell us about social structure, parental behavior, daily ranging, how juveniles survived. The fossil record is largely silent on the animal as a living system inside an environment. And the deepest gap isn't about dinosaurs at all. Why does bone have the material properties it has? That question goes down through hydroxyapatite crystal structure, into quantum mechanics of chemical bonds, into why the fundamental constants, the strength of electromagnetism, the mass of the electron, have the values they do, there the answer is, we don't know. We measure the constants with extraordinary precision. We cannot explain why those values rather than others. That's where explanation ends. The job is to push that endpoint as deep as possible. It's been pushed very far. Some residual remains, and it will probably always remain. So here's the answer to the question we started with. Not how big were they. That question has an answer, and the answer is large, and the answer is not interesting. The interesting question is, how were they possible? And the answer is this. They were possible because the physical constraints on large land animals, while severe, admit at least one solution. That solution requires pneumatized bones, columnar limbs, elevated metabolism for sustained activity, and a cardiovascular system capable of generating pressures we can calculate precisely but not directly observe. Every one of those features is forced by physics. Biology found them through selection pressure. Physics required them through geometry and material properties, and the gravitational constant that hasn't budged in 4 billion years. The largest land animals that have ever lived were operating at the edges of what the laws of nature permit. Bone stresses near safety limits, body masses near the theoretical maximum, cardiovascular demands near whatever ceiling biology could reach. They were, in a specific technical sense, optimal, not because anything designed them, but because selection pressure removes everything that doesn't work, and when constraints are tight enough, what's left is a very small set of things that do work, and everything in that set looks like it was engineered. It wasn't. But physics doesn't distinguish between engineering and evolution. Both are subject to identical constraints. Both produce solutions that obey the same equations. The skeleton in the museum is not a monument to how impressive nature is. It's a set of simultaneous equations in 3 dimensions, preserved in stone, waiting for you to read them. The equations have solutions. The solutions are the animal. The animal was real, it worked, and the numbers balance. That's not wonder. That's something better than wonder. That's understanding.